NMR. So the nuclear magnetic resonance spectroscopy. Just 1 minute. Okay, so the basic concept of NMR spectroscopy according to its syllabus. So by the proton NMR spectroscopy, chemical shift and its measurement, factors influencing chemical shift, all these things we'll discuss. Then if time permits, then we'll move to complex NMR spectra like NOSI, COSI, okay, or ROSI is there here. Then application C13, okay, let's hope we can't cover all these things. So the nuclear magnetic resonance, so that indicates, you see, the nuclear magnetic resonance. Each word is having its significance. Nucleus, as we know, is positively charged. So when it rotates, so when any charged particle is accelerated, an electric field will be developed. So, and electric field is associated with magnetic field. So when external magnetic field is applied, then this magnetic field or of proton that will make resonance with the external magnetic field. So that is the principle behind the nuclear magnetic resonance. So this involves the interaction between an oscillating magnetic field of electromagnetic radiation and the magnetic energy of hydrogen nucleus or some other type of nuclei. What are the other type of nuclei that we'll see? If so, the other types of nuclei means if there will be odd number of protons, the nuclei which contains odd number of protons, so they may make resonance with the external magnetic field. So the sample absorbs electromagnetic radiation in radio wave region at different frequencies. So since absorption depends upon the type of proton of the sample. So now we'll discuss this nuclear magnetic dipole, the spinning proton. Proton in the sense it is having only one, means the nuclei which contains only one proton in case of simple hydrogen atom. So the spinning proton, when it will spin, it will have two types of motion. It has a spinning motion and it's having on gyrational motion or precessional motion. As you can, uh, this type of motion is observed in case of a spinning top. When your top spins, it will have its spinning motion and also the gyrational motion or precessional motion. That is also known as gyroscopic motion. So that means the axis that will make it will rotate like this. It will spin. You can imagine the top when it spins, so it rotate around in its own axis, but the axis makes a motion like this. So that is known as the precessional motion or precessional orbit here, or it is gyroscopic motion. So let us consider a particularly small magnet spinning in an external field. It has been found that the proton presses about its axis of the external magnetic field. So you can see this one, the spinning motion and precessional motion. So it is like this. So the gyroscopic process, so it precesses under the influence of the gravity. So therefore it is found that omega, the angular precessional velocity, that is equal to the gyromagnetic ratio gamma into h naught, that is the applied field in gas, the magnetic field. So omega equal to gamma h naught, and gamma, the gyromagnetic ratio, that is equal to 2 pi mu divided by hi. So mu is the magnetic moment of the spinning bar magnet, I is the spin quantum number of the spinning magnet, and h is the Planck's constant. So according to the fundamental NMR equation, gamma h naught will be equal to 2 pi nu, where nu is the frequency of electromagnetic radiation. So that indicates, so angular precessional velocity omega equal to 2 pi nu, because gamma h naught will be equal to omega. So the value of this frequency inserted is called the precessional frequency. The precessional frequency may be defined as the number of revolutions per second made by the magnetic moment vector of the nucleus around the external field h naught. Alternatively, the precessional frequency of the spinning bar magnet may be defined as equal to the frequency of the electromagnetic radiation in megacycle per second necessary to induce a transition of spin from one state to another state. So now you can see which will have the spin quantum number. You can see if mass number, any nuclei, it will carry a charge, so they will possess spin angular momentum. The moment of spin angular momentum, it is quantized, so only those nuclei which have a finite value of spin quantum number, that is I is greater than 0, will precess along the axis of rotation. So you can see if the mass number and atomic number can now correlate. If mass number and atomic number both are even, second one I'm telling, mass number is even, atomic number is even. Atomic number means number of protons, even number of protons and even number of neutrons. Then mass number and atomic number both will be even. Then the spin quantum number will be 0. If mass number is even but atomic number is odd, that means odd number of protons are there and odd number of neutrons are there, then odd or mass number will be even and atomic number will be odd, then spin quantum number will be 1 2 3 like this. But if mass number is odd, that means number of protons and neutrons will be odd and atomic number is either odd or even, then spin quantum number will be half, 3 by 2, 5 by 2 like this. So if a proton is placed in the magnetic field, then what will happen? So in the absence of magnetic field, this is the gyrational motion of the or precessional motion of the proton. So when external magnetic field is applied, then what will happen? The motion, it will be opposed in the, that means high energy. It will flip from this position to that position in the presence of the external magnetic field. If a proton is placed in a magnetic field, then it starts precessing at a certain frequency in the radio wave region and thus will be capable of taking up one or two orientations with respect to the external magnetic field. So it may alignment with the field or alignment against the field, what has been shown here. It may have directional or precessional motion like this, or it may be in the opposite. So it will have opposite means it will have high energy. If it is aligned along the magnetic field, then it will have low energy. So if a proton is precessing in the aligned orientation, it can pass into the opposed orientation by absorbing energy. That means to the higher energy state, it will move by or it will jump by absorption of energy. From the high energy opposed orientation, it comes back to the low energy aligned orientation, more stable by losing energy. This transformation from one energy state to another is known as flipping of proton. So the transition between the two energy states, so has been shown here. So it can be brought about by absorption of a quantum of electromagnetic radiation in the radio wave region with energy h nu. So this is the theory behind the nuclear magnetic resonance. Okay, sorry, I was attending a phone call. So that means now the proton, by absorption of external energy or external electromagnetic radiation, it will flip from lower energy state to higher energy state. So depending upon the external electric field, there will be resonance or external electromagnetic radiation. There will be resonance between the magnetic moment of the proton and the external magnetic field. So now the relaxation process, it involves some non-radiative transition by which a nucleus in an upper transition state returns to the lower spin state. So the relaxation process are, it may be spin relaxation or spin lattice relaxation or quadrupole relaxation. In spin relaxation, it is due to the mutual exchange of spins by two precessing nuclei which are in close proximity to each other. It means they will interact with each other. That is spin relaxation. This proton may interact with the spin of the nearby proton. We know that each precessing nuclei is associated with a magnetic vector component rotating in a plane perpendicular to the field. If this small rotating magnetic field is in the same as is required to induce a transition in the neighboring proton, so the mutual exchange of spin takes place. That is spin relaxation. Next is your spin lattice relaxation. Lattice means where in the it involves the transfer of energy from the nucleus in its hydrogen state to the molecular lattice, not to another proton or another nuclei. It will relax the energy to the lattice as a whole or to the molecular. So that is spin lattice relaxation. Then quadrupole relaxation. It is a prominent relaxation process for nuclei having the spin quantum number is greater than half, such as nitrogen 14, oxygen 17, boron 11. So due to anisotropic interaction between non-spherical electrically quadrupole nuclei and the electric field. Now moving towards the number of signals. The number of signals in NMR spectrum tells the number of different sets of equivalent protons in a molecule. Little bit idea I have given in the previous class that we have to find out the protons, symmetrical protons. For example, in this case, we have acetone. You can see here the CS3 and CS3 both are just alpha position to this carbonyl group. So both these six protons are there and they are symmetrical. They are magnetic equivalent. So it may be noted that the magnetically equivalent protons are chemically equivalent. So the two six protons are chemically equivalent. So they are also magnetically equivalent. So that's why we'll get only one signal for acetone. Where we'll get that we'll discuss. Similarly, in case of cyclobutane, so eight protons are there, eight hydrogens are there. They are also chemically equivalent and magnetically equivalent. So we'll get only one signal. Similarly, benzene, tetramethyl methane, acetone, all will give a single signal, one signal only. So it has been written here. In acetone, all the six protons are exactly similar environment, therefore only one signal is observed. In case of this one, methyl alcohol, you can see is methyl proton, three methyl proton, one type, and one hydroxyl proton, OH. So this is other type. So number of signals we will get two NMR signals. In case of it is ethylamine. So this nitrogen is having two proton, carbon it is having two proton, and this three proton. These five protons are not equivalent because this carbon is linked to one carbon and one nitrogen. So we have to see where to which the proton is attached and what is which element is in its neighbor. So this proton, if you consider, which is the methylene group, two protons. So to this carbon, we have one methyl group and one amine group. So these two protons are different from these three protons because here this carbon is attached to only another carbon. So environment is different. So this is three protons one set, these two protons other set, and this amine group two protons are also the third set. So that's why we'll get three NMR signals. In this case, you consider this CS2, this is CS2, but they are in different environment. This because this A, what I will mention here, the carbon denoted by A, it is attached to chlorine and here attached to carbon B. But carbon B is attached to carbon A and carbon C. And carbon C is attached to only one carbon, that is carbon B. Therefore, these two protons are different from this and different from this. So three types of protons are there. So we'll get three NMR signals. In this case, if you consider isopropyl alcohol, one hydroxyl proton and one environment. This secondary carbon which is there, the C1, that is another environment because this carbon is attached to oxygen, carbon and carbon, and this methyl group proton, it is attached to this carbon, this methyl also attached to this carbon. These six protons are one type denoted by B, and this one proton is a second type denoted by C, and this hydroxyl proton is another type. Okay, so three types of protons, so three signals. Would you follow what I am telling? All of you are there?
Sir.
Yes, sir. Yes,
Oh,
sir.
okay, okay. So like this, you can find out the number of signals. This methyl succinate, so this methyl group one type and these two methylene groups, they are also other types. So we'll get two signals, NMR signals. Here also two because the environment is different. This carbon is attached to C, but this carbon is attached to oxygen. So two environments, so two signals. And here these four protons, one type because this carbon is attached to methyl, another carbon. This carbon is attached to methyl and another carbon. So these four protons are one type and these methyl protons are other types. So we'll get two signals. Similarly, if you consider this one, 2-chloropropene. So you can see here, this is one type of proton, and these two hydrogen which are attached to the carbon double bond, so they are of different because this is cis to chlorine and this is trans to chlorine. So these two protons will get two signals. Okay, so because carbon as you see, hydrogen B and hydrogen C are not in exactly similar environment, so two signal for this and this for these three protons one signal, so we'll get three signals. Yes, in this case methyl cyclopropane, how many signals will be observed? For methyl group one and for ethyl group, sorry, this hydrogen another one, but here two hydrogens are there. These two hydrogens will get two signals because you can see here this hydrogen is the cis 2 methyl group and this is trans. So these two hydrogens are not in the same environment, but this is same ASS. Okay, clearly understood, I think. So for this one signal, for this other signal, this is third and this is fourth. We'll get four signals for methyl cyclopropane. 1,2-dichloropropane. You consider 1,2-dichloropropane, methyl group 1, but this yes, 1,2-dichloropropane. This is methyl cyclopropane. It is 1,2-dichloropropane. Yes. In this case, we have to check the chirality because this carbon is attached to four different groups. So in that case, we have to find out the maybe in cis or transposition you can say, or it is Gooch or eclipse. In that case, these two protons are in different environment because one may be nearer to this one may be further. Or if you consider it one may be cis, one may be trans. So these two are different. It's not mentioned here. A is mentioned, but one is A, another is B. And this hydrogen is different, and methyl again different. So four signals will get. So like this, so many examples are there. You can go through that one. Okay, then the instrumentation part. So as already I have discussed in the theory, we should have an external magnet which will produce the magnetic field. So the nuclear magnetic resonance spectrophotometer makes use of a magnet, a radio frequency generator, a detector, and an amplifier. The detection system is used to note that energy is being transferred from the radio frequency beam to the nucleus. The sample under investigation is taken in a glass tube, which is placed between the pole faces of a magnet, okay, and a radio frequency source of frequency 60 megacycle or 60 megahertz. Nowadays, we are using the FTNMR also for your transmission, maybe 300 megahertz or higher frequency. This is 60 megacycle per second or 60 megahertz is the older one. Okay, so radio frequency source is made to fall on the sample. It can be done by feeding energy or radio frequency source into the coil, which is wound around the sample tube. So here the signal will be detected if the nuclei in the sample resonates with the source. So change in energy required to flip the proton in the same is the same as that of the source. So energy transferred from the source via nuclei to the detector coil. Okay, then it will be recorded in the chart paper. Not chart paper, it is in computer. Okay. So now where we'll get the signal, that is the chemical shift. The number of signals in an NMR spectrum tells the number of sets of equivalent protons in a molecule. So we know how many peaks or how many signals we will get, but where we will get, that's the thing. The and how will you measure? What we will measure here? The position of the signals in the spectrum helps us to know the nature of proton. That means it may be aromatic, aliphatic, acetylenic, vinylenic, adjacent to some electron attracting or electron releasing groups. So each of these type of proton will have different electronic environment as already we know. And thus they observe at different applied field strength. So it is important to note that it is the electronic environment which tells where a proton shows absorption in the spectrum. Now, the electronic environment means the electron density, whether it decreases or it increases. That means the spinning of the proton, it depends upon the electronic environment, means the electron density. Okay, so when a molecule is placed in a magnetic field, its electrons are caused to circulate, and thus they produce secondary magnetic field or induced magnetic field, because proton is charged, so nucleus is charged, so it produces magnetic field, and electrons are also revolving, so they will also produce a magnetic field, that is induced magnetic field or secondary magnetic field. So what will happen, these magnetic field of the nucleus and magnetic of the field of proton, sorry, electron, they may oppose or they may enhance. So that's why the spectrum or the peak position where we'll get, so that will change. And depending upon the environment, each type of proton will give a specific absorption or resonance at a specific field strength. So rotation of electrons about the proton itself generate a field in such a way that the proton, it opposes the applied field or it may enhance both. Thus, the field felt by the proton, in this case, okay, it opposes. When it opposes, the field felt by the proton is diminished or it decreases, and the proton is said to be shielded. Would you follow this one? Shielding and deshielding, two things are there here. The rotation of electrons, okay, that will again
Pardon,
exhibit.
sir. Sir,
Yes.
sir,
Hmm.
screen
Hmm.
vanished, sir. Screen is not
Hello.
visible anymore. Sir, screen is not visible anymore.
Oh, okay, I have to share it again. Network problem maybe. Is it okay now?
Yes, sir.
Okay. So what is shielding that we are explaining? That means
Shielding
let
and
us
answer.
Mm-hmm. Hello.
Yes, sir. We can hear, sir.
Okay. Now what? I thought you were telling something. So thing is here, when a molecule, if as a whole, we are taking the NMR spectra of the molecule, not the single proton. Okay. So when we place the molecule in the magnetic field, electron also spins along with the proton. So we are measuring the resonance energy of the proton with the external magnetic field. And resonance energy means at what energy the that will match with the magnetic moment of the proton. So when electrons are also there, so they are also charged. So when they will spin, the rotation of electron about the proton also generate a field. So when this field opposes the applied field in such a way that at the proton, the field, that means electric field due to the electron, that opposes the applied field. So what will happen? The field felt by proton will be less in comparison to if electron will not be there. How much field will be felt by the proton? If electron will be there, due to their field, they will oppose the applied field. So the field felt by the proton will be diminished or it will be decreased. And at that time, we will tell that the proton is said to be shielded. Rotation of electrons especially pi electrons about the nearby nuclei, generate a field that can either oppose or reinforce. Two things. In some cases, it will oppose only, then the said proton means the particular proton, it will be shielded. But when there will be pi electron, that means in pi electron means it will be double bond or triple bond. In general, it has been written here. In some cases, that will enhance, and in some cases, that will oppose. Two things will be there. So when the if the induced field opposes the applied field, then the proton is said to be shielded, already we know. But if the new induced field reinforces the applied field, means it will be more, then the proton feels higher field strength, then proton is said to be de-shielded. Okay, so shielding means it will feel less magnetic field. De-shielded means it will feel more magnetic field. That is the thing. So shielding shifts the absorption of field. So it will absorb at, if it is shielding, it will absorb lower energy. At lower energy there will be resonance. So that is known as off field. We'll so see here two scales are there. What is off field and what is down field? We have to we'll discuss in the next uh, subsequent pages, I think. And see, shielding shifts the absorption upfield, and de-shielding shifts the absorption downfield to get an effective field strength necessary for absorption. So such shifts, it will be compared with a standard reference. That means reference means which will have some equivalent type of proton. We'll see what are the references in the position of NMR absorption, which arise due to shielding or de-shielding protons by electron, is called chemical shift. Okay, these shifts compared to a standard reference in the position of NMR absorption, which arise due to shielding or de-shielding of protons by electrons, are called chemical shift. So for measuring the chemical shift, we have to take a standard. So here we have taken the tetramethylsilane as the reference. Tetramethylsilane in silicon, 4 methyl groups are there, and 4 set of protons, 4 methyl groups, all 12 protons are equivalent. Okay, so tetramethylsilane is taken as the reference, and the chemical shift, the value for tetramethylsilane is taken as 0. Two scales are there. We'll discuss that one. Okay, one is the delta value, one is the tau value. Tau is 10 minus delta. We'll discuss that one. First, let us see this one. Sorry. So tetramethylsilane is taken as the reference. So due to the low electronegativity of silicon, the shielding of equivalent protons in tetramethylsilane is greater than most of the organic compounds. The shielding is high. So therefore, we have taken tetramethylsilane as the reference, and the NMR signal for tetramethylsilane is taken as the reference, and chemical shift of different kinds of proton are measured relative to TMS or tetramethylsilane. So clearly the NMR signal for a particular proton in a molecule will appear at different field strength compared to the signal from TMS. So this difference in absorption position of the proton with respect to TMS signal is called chemical shift or delta value. So it is not measured in Gauss, but it's measured in equivalent frequency unit, which is then divided by frequency of spectrophotometer or spectrometer used. This gives the value delta. So you have written, you can see here the resonance frequency of the sample, and it's the resonance frequency of TMS. So the value of delta of a substance with respect to TMS can be obtained by measuring the frequency of sample and that of TMS. So divided by operating frequency in megacycle, that is in delta. Delta. So del V del nu, the difference in frequency divided by operating frequency. So generally it is having value 0 to 10. The most chemical shift have delta value between 0 and 10. In tau scale, another scale, it is 10 minus delta. Signal for standard reference, TMS is taken as 10 ppm. Okay, in delta it is 0. See here, in delta is 0 and it is not gamma, it is tau value. Tau is 10. So like that, reverse one. High shielded signals, this is upfield. Low delta value means upfield, high delta value is downfield. Deshielded downfield, shielded upfield. Like this you have to remember. Deshielded downfield, DD, and shielded upfield. So downfield means low higher delta value or lower tau value. Greater the deshielding of proton, larger will be the value of delta. Greater the deshielding, larger the value of delta. So now the internal standards. Reference materials which are commonly employed as internal standard. Two types of internal standards are there. One is tetramethylsilane, another is sodium salt of 3-trimethylsilyl propane sulfonate. But commonly tetramethylsilane is used as the internal standard. It is generally employed as internal standard for measuring the position of proton C13 silicon 29 in NMR spectroscopy. Main merits is it's chemically inert and miscible with large range of solvents. Its 12 protons are magnetically equivalent. It is highly volatile and can be easily removed to get back the sample. It does not take part in intermolecular associations with the sample. Its resonance position is far away from absorption due to proton and in most organic molecules. So assigning TMS value, delta value is 0, a scale can be derived which is most of the proton resonance are of the same side. So this is the types of proton and chemical shift values are given, delta value and also tau value. Tau is nothing, it is a delta equal to 10 minus tau. Already we have shown here. Tau equal to 10 minus delta or delta equal to 10 minus tau, whatever may be. Now the shielding and deshielding effect, how it happens. So hydrogen nuclei in a molecule, as we know, surrounded by electronic charge, which shields the nucleus from the influence of the applied field. Thus, to overcome the shielding effect and to bring the proton to resonance, greater external field is required. Clearly, greater the electron density around the proton, greater will be the induced secondary magnetic field. So, which opposes the applied field and thus greater external field will cause proton absorption. The extent of shielding is represented by in terms of shielding parameter alpha. So H, when absorption occurs, the field H felt by the proton is represented by H equal to H naught into 1 minus alpha. where S naught is the applied field strength and H is the field which is felt by the proton. Alpha is the shielding parameter. So greater the value of alpha, greater will the value of applied field strength which has to be applied to get the effective field required for absorption and vice versa. Okay, now let us see the carbonyl compound. So how deshielding of aldehydic proton takes place is the aldehyde proton. Any other, let it be R alkyl group. Here is one proton and here is the carbon oxygen double bond. So how the deshielding occurs, you see. This is the magnetic field of the proton due to electron, and this is the magnetic field direction. So and other thing is the acetylene case. Where is acetylene? This is perpendicular to carbon oxygen double bond, but in case of acetylene, if you compare, it is just parallel. You can see here, here acetylene. So in this case, it will be shielding of acetylene proton, but in carbonyl, it is deshielding, just perpendicular. If you compare these two, you should know here deshielding occurs in aldehydic proton. Similarly, in ethylene also deshielding occurs, double bond, ethylenic proton deshielding. In acetylene, it will be shielding in the same direction, and in case of benzene, ring current. So in case of diamagnetic and paramagnetism will be there. So it will ring current both. So an excellent example of shielding and deshielding by ring current. So in annulenes, the proton outside the ring in annulenes are strongly deshielded, and those inside the ring are strongly shielded. Here, in case of annulene. Which are outside the ring, they are strongly deshielded, and those are inside, they are shielded. Other factors which affects, that is hydrogen bonding. So solvent which are used in NMR spectroscopy, all of the solvent should not contain proton. If proton will be there, then if hydrogen will be there, then it should be deuterium, not hydrogen, because proton absorbs in NMR region, radio wave region. But if deuterium, that means two protons are one proton and one neutron is there. Now mass number is even, then it is not absorbed or make resonance with the external magnetic field. So deuterated samples can be used, or the solvent which don't contain any hydrogen, like carbon tetrachloride, carbon disulfide. Here it is deuterochloroform, CdCl3, and hexachloroacetone. No proton is there. Here deuterium is there, deuterated solvent or deuterated chloroform, carbon disulfide and carbon tetrachloride. So these are the solvents which are used in NMR spectroscopy. dimethyl sulfoxide, deuterated dimethyl sulfoxide can also be used. Anyway, so these are the solvents which are used, and corresponding peaks are also given. And peak area and proton counting, so that is the integration. We have to find out the peak area, that is the integration, how to find out the peak area. We have, let this is the peak, this is at the peak, so we have to take the integration, we'll have to find out the peak area. So then we'll get the number of protons in the ratio we have to find out. So if you consider the spectrum of toluene, where it is given. Okay. In NMR spectrum, various peaks represent equivalent set of protons. The size or area of each peak tells the number of proton in each set present in the compound under investigation. The area under an NMR signal is directly proportional to the number of protons giving rise to the signal. For flipping over a proton, a quantum of energy is observed in the same effective magnetic field. So, greater the number of protons that flip over a particular frequency, greater will be the energy observed, and greater is the area under the absorption peak. So, number of protons will increase, the peak area will increase, and this is one number of signal, then peak area, broadness of the signal, and another thing, type of signal or splitting of the signal, how it splits, whether it is single signal or it is a combination of more signals, so splitting of signal. So this tells, it is already pointed out that each signal in an NMR spectrum represents one kind or one set of protons in a molecule, and it is found that in certain molecules, a single peak is not observed, but instead a multiplet. That means single peak means singlet is not observed, but a group of peaks or multiplet is observed. For example, if you consider this one, bromoethane or ethyl bromide, in this case, we have two different set of protons. Here, three protons of one kind and two protons of other kind. So now what will happen when you are getting the peak for proton B, that will interfere with the neighboring proton. So what will happen is this molecule has two kinds of protons in it, and thus two signals are expected in its NMR spectrum. Clear, already we have discussed. It has been observed that for each kind of proton, we don't get a singlet, but a group of peaks are observed. For a kind of proton, A kind, that means three proton, a triplet, that is a group of three peaks is observed, and for B proton, we'll get a quartet, that means group of four peaks will be observed. So for B, we'll get four peaks quartet, and for A, we'll get a triplet. So you can see here, this one you can see, we are getting a triplet here. This is for the methyl group, and here a quadrat, four peaks are there. This is for the methylene group. Okay, so signal what will get, you see a three proton triplet, that means this group, three proton triplet at tau value 8.35, and a two proton quartet at a value tau value of 6. This is tau is in 10 ppm, delta value is reverse. Okay, and at 10 we'll get the signal for TMS. Similarly, if you consider this one, CHCl2 CH2Cl 1 2 112 trichloro 112 trichloroethane. So see these two sets of protons. Yes. So two signals will get here, a two proton doublet For A, we'll get a 2 proton doublet, and for B, we'll get a 1 proton triplet. 2 proton doublet means the peak area will be just 2 proton. Number of protons mean it tells about the peak area. Peak area will be more. 2 proton, yes, 2 proton doublet, and here it will be 1 proton triplet. 1 proton. So definitely this peak area will be twice than this peak area. Okay. Now spin coupling. How it will couple? It is, you can see. So why we'll get this doublet and triplet? So that is due to spin coupling. The spin of one proton that will interact with the spin of the neighboring proton. So due to spin coupling. So let us, to understand it properly, let us consider a molecule ethyl bromide CH3 CH2 Br. So the spin of two protons of CH2 can couple with the adjacent methyl group in three different ways. How? Two protons, when it will couple, both may oppose, or first may be in this direction, second in this direction, or first may be this one, second is this one, which will not affecting, and here it will reinforce. So okay, so that's why what will happen, there are two proton, so in three different way they will interact. So three different way can be alignment are like this. So thus a triplet of peak results with intensity 1 is to 2 is to 1. If this is 1, this will be 2, this is 1. 1 is to 2 is to 1. If it is triplet, it is 1 is to 2 is to 1 ratio. Always it will be. So similarly, the three methyl protons, they may interact with the adjacent methylene group. So three protons how will interact? All are opposing in the same direction. You can think this is strongly opposing. Two may be opposing, one reinforcing. So in different way. First, second opposing, third reinforcing, first opposing. So no need to tell you, just see. This may like this, or in this case, two are reinforcing, one is opposing. So weakly, this is weakly opposing, this is weakly reinforcing, this is strongly reinforcing. So four alignments will be there. So 1 is to 3 is to 3 is to 1 ratio. The quartet of peaks results with an intensity ratio 1 is to 3 is to 3 is to 1, which corresponds to the distribution ratio of all alignments. So how will you get then? Then it is the binomial expression. 1 plus x to the power n. We know that one plus x square. If n equal to 2, then it is 1 plus x square. 1 plus 2 is x plus 1. So one coefficient we have to take 1 is to 2 is to 1. If it is 3, then it is cube. The coefficients 1 is to 3x square, 1 plus 3x square plus 3x plus x cube. So coefficient will be 1, 3, 3, 1. Okay, if it is 4, then we'll get a quintet or pentet, whatever it may be. So they will be in the ratio 1 is to 4 is to 6 is to 4 is to 1. So how to do the triangle will be there here. Then let me check. Yes, so given here to find out the ratio, you should think on this one. 1, then 1 is to 1, 1, so 1 is to 2 is to 1, 1 is to 3 is to 3 is to 1. Okay, 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 4. So 1 is to 4 is to 6 is to 4 is to 1. Then 1 plus 4 5, 4 plus 6 10, 4 plus 10, then 5. So 1 is to 5 is to 10 is to 10 is to 5 is to 1. If it is a sextet. Okay, so this is the peak area ratio. So now we'll move towards the some problems. Proton exchange coupling constants are not there. Yes. Some important NMR spectra. Phenylacetylene. So what are the different types of proton? What are the different types of proton here? This is one acetylenic proton, and these five they are of same. So we'll get a one proton singlet, and these five protons will get a multiplet. So 5 proton unsymmetrical multiplet, which is from 2.4 to 2.8, and 1 proton at 6.95 tau value. Similarly, for propyl alcohol or N-propanol, how many types of protons? Environment, this is one, 3 protons of one type, and these 2 protons they are attached to CH3. CH3, what? One is CH3 and one is CH2, and that CH2 is attached to alcohol group. So this is also different. So 1, 2, 3, 4 types of protons. So we'll get 4 signals. Okay. So 4 signals. This is a one hydroxyl group. So 1 proton, and this is 2 proton. You can see 2 proton. Neighboring is only 2 proton. So these 2 proton will get a triplet, and these 2 protons will get 5 plus 1, that means sextet, and this for this 3 proton will get a triplet. Okay, that means how in neighboring carbon atom or in the neighborhood how many protons are there, you add 1 to the sum of the protons, you will get that type of peak. If in neighbor 2 protons are there, you will get a triplet. 2 plus 1, 3. If 3 protons are there in neighbor of the proton which you are considering, then it will be a quartet. Okay. So in this case, we are considering the OH, and because this is oxygen which is more electronegative, so we'll get this is the one proton only. So one proton singlet will get. It is a hump, this one. 7.5 or 7.7, whatever we'll get, that is due to the hydroxyl proton. Okay, and that methyl proton, you can see this, you can say the 3 proton triplet. 3 proton triplet, it will come around 9. So it is 9.1. In the delta value, it will be less than 1. Okay, and this 2 proton sextet, so that will be little bit uphill sextet. So at 8.45, then the hydroxyl hump, then the 2 proton triplet, this one, more electronegative, so more decelerated, so down the field, so CS2, 2 proton triplet around 6.4. Are you clear? Okay, next molecule you can take
Okay.
the metacresal. Yes, metacresal. Here one hydroxyl or phenolic OH group, that is one proton, one methyl proton, and these 3 protons. 1, 2, 3, and 4. These 4 protons, they are unsymmetrical, but for them we'll get a multiplet. The ring proton 1, 2, 3, 4. This methyl one signal, hydroxyl proton second signal, and the ring proton will get a multiplet for this one. So which is downfield again because it desilted. So hydroxyl OH proton, the singlet will get around 4.32, this one, and this methyl group proton, 3 proton will get the singlet around 7.5 or 7.75, and for the 4 proton non-symmetrical will get around 2.75 to 3.5. Now coming to the carboxylic chlorocarboxylic acid, the chloropropanoic acid. In this case, you consider you have a carboxylic group proton, and this is another type of proton, and this is one. So three. So three signals will get. So this carboxyl group, that proton will get a singlet which is off the scale. Off the scale means it will be in the negative. Okay, here somewhere minus, and one proton quartet. This one proton quartet, 3 proton in the neighbor, so 3 plus 1, 4. So one proton quartet around 5.5, and 3 proton doublet, 3 proton doublet around 8.25. Next, if you consider that is the NMR spectrum for anisidine, methoxy, paramethoxy, aniline or anisidine. So here NH2 groups, NH2 proton is there, methoxy proton is there, and the benzene ring proton. So 3 signals will get. So a 2 proton singlet, 3 proton singlet, and 4 proton unsymmetrical pattern. This one, 4 proton unsymmetrical, that is 3.45 to 3.2, and the 3 proton singlet will get around 6.25, and the 2 proton singlet for amine group 6.6. Would you follow? Now next one, the amide. In case of amide, you will get a 2 proton singlet, which may be the hump, and a 2 proton, this one 2 proton 3 plus 1 quartet, and 3 proton triplet. So 3 proton triplet around 8.85. Here 3 proton triplet, then 2 proton quartet around 7.7, and a 2 proton hump around 2.9. Here this one, for this amide proton, NH2 proton, you will get a hump around 2.9 to 4. This is for amide. For propane 1OL, propine 1OL. Just 1 minute. Yes. So if you consider this one, then one hydroxyl group, so one proton singlet, For hydroxyl, then two proton. This one, two proton singlet and one proton again singlet, oral singlet. So one proton singlet, this one at around 7.5. Then one proton singlet for OH around 7.15, 7.5, 7.15 and 5.65. So two proton singlet or nearly doublet. So parabromophenol, 1, 2 and ring proton on symmetrical. So 4 proton on symmetrical pattern, doublet, 2.6 to 3.4 on symmetrical. Then this one is the quadret, 2 proton quadret and 3 proton triplet. Generally, methyl group will come around 8 to 9.5 or 8.5 or 8 to 9.5. Methylene group will come here. Okay, so it depends upon the compound. What are the environment? That does not mean that you'll get the peak methyl group peak or methylene group peak you are getting here means in every compound you will get here. It depends upon the environment what is there. Okay, and in any case you have to just match it with the standard. If your sample you are for any unknown sample you are taking the NMR, then you have to match with some standard. And for NMR, when you are taking the NMR, you should know the probable structure of that compound. They will ask if it is an unknown compound. When you are taking the some NMR, you will be asked what is the probable structure. Then only they will exactly they can interpret. Okay. Then this one chloro and bromo, three bromo, sorry one bromo three chloro propane. So how many types of proton? Three types of proton. So three signal, two proton pentate, two proton pentate. This one first at 7.65. Then two proton triplet, two proton triplet. These two, and chlorine and bromine. Only electronegative difference. So they will nearly come near to each other. So it is giving a sextet type of thing. 6.2 and 6.48. They intermix with each other. Okay, so it is a triplet, not sextet, not one peak. This is two peaks. Now coming to the next one, any carboxylic acid is benzaldehyde of the scale again. So benzaldehyde to consider. So you have the aldehyde proton and the ring proton. So for aldehyde proton, you will get the singlet, which is of the scale 0.15 here somewhere, and for 5 proton on symmetrical pattern, this is for the ring proton, and this one of the scale they have taken it here. Just they have bring this one to here because the of the scale, so it is in there because it starts from 2 to 10. So you will get the peak singlet peak for aldehyde proton around 0.15. Next 2 3 diagram of propene. So these two protons are different. They are one is cis, one is in transposition, and these two proton are different. So totally three peaks. One proton singlet, sorry, this is another proton. So one proton doublet, because this is the neighboring proton. They are the different environment, so they will resonance. So for this you will get a doublet. For this also you will get a doublet. So one proton doublet, which is at cis. Okay, so you'll get 3.98 and one, and another is 4.38. Okay, the cis is more desilted. It is more electronegative. Bromine is at a cis position, so it is more desilted, so more downfield. Okay, so 3.9 it is for cis and 4.38 is for trans, and this is a two proton singlet, which will be more electronegative, so around 5.8 or 6 it will come. Okay, then this is acetaldehyde, so 3 proton you will get 3 proton singlet and a 1 proton which is off the scale. So 3 proton, sorry, H is the CHO, so 3 proton doublet at 7.8 and 1 proton quartet at 0.15, which is off the scale. So these are the examples. You may go through all the examples what I have shown to you, or I have shared with you the book. So next we'll see some problems and mass spectroscopy, and some problems will solve those things. Okay. So hope 21st we will meet. Happy Diwali to all of you.
Same to you, sir.
Thank you.